property that the Dirac delta will be activated when P is equal X, when Q is equal Y, and S is equal Z. Okay? They are independent. These X, Y, and Z are independent. Okay? So this integral over here gives me U, X, Y. This is solution of this integral over here. Now, look at this. Finding or solving is better, okay? Solving for G, this implies the solution U, X, Y, and Z, since the source F, okay, let's plug here, Q, S, is given, or it is known. You see, this is known. Okay? Now, if I solve it what? Okay? This sub-problem. What is the sub-problem? Laplacian of G is equal delta P minus X delta Q minus Y delta S minus Z. Okay? Now, G of S is equal to 0. This is Laplacian. Okay? So, I solve for G, okay, and plug on this integral over here, and I get the solution. You see? That's the idea. Okay? Why do I use this delta of Dirac? Okay? And that's very, very interesting, because this operator here, to be formally self-adjoint, the left-hand side, it's 0. Okay? As I mentioned before. The same idea I used for the previous video, where I started, the previous video, I started exactly like G, in this case, number U is equal U, let's put the V, let's put the Laplacian here. Okay? That's what I did before. Okay, this is instead of VG. Okay, then here, for one dimension, okay, I related a sub-problem as delta of for one dimension. Okay, I use this Dirac delta here, and I solve for G. Okay, and to get this, attention now, this is F. In this case, okay, F of X. Okay, G of F of X, this is an integral, exactly as I did before. That's why the gain function is related. Okay, and this applied to U, this gives us U of X, which is the solution for one dimension, okay? For one dimension. That's actually what I did before. We will do some exercise, okay? I will apply this to get the solution of Poisson equation for 3 dimensions, and also give an example used for 1 dimension, okay? Then I finalize all these videos, just for you to understand, okay, what are you using and why are you using, okay. I write down, okay, what is important, why G, the green function, is important, because it substitutes the left hand side by impulse, okay, delta, the Dirac delta Dirac, okay, they are impulse, okay, which is common, it's very, very common, is usual in the application in mechanical engineering, electronic engineering, civil engineering, okay. You break down, look, you break down F as impulses, okay, and to solve for G, okay, and substitute on this integral here, because F is known, okay, is given, okay, F is known, okay? And G, I will solve this equation over here, okay, in this sub-problem, okay. This I break down, look at here and look at here. Let's see, I broke down F, okay, in impulses. Those are impulses. And this is the property of delta of Dirac. Did you understand? It's clear, okay? Then I will solve the Poisson equation, okay? And then I'll give an example using this and substitute, okay, the Laplacian of the green function for 1G, okay, related to this impulse, okay? That's clear. Again, I repeat, okay, now you go to the literature, say you understand when the video starts, okay, write down the self-adjoint, okay. To be self-adjoint, okay, you must impose this over here, okay. The boundary condition U is given, G is not given, okay. You impose G at the boundary S to be 0, just to get the left hand side is equal 0. Consequently, okay, you have a self-adjoint operator. Okay? That's a very, very, very important, okay, consideration. Okay.